Up here on the board, I have 3 different versions of an exponential growth curve. Show of hands, how many of you have seen this curve before? Awesome. Okay, so similarities and differences of these curves. Okay, what do they have in common? Yeah.
The shape is common.
The general shape is common. Okay, yeah. Very good. They all, as you read them, right, because we read a graph from left to right, they are all increasing. Are they all increasing at the same rate? No. So these are the 3 graphs right here. I've got 2 to the power of x, 3 to the power of x, and 5 to the power of x. So what's happening here is that the red one is doubling. As I increase the x value by 1, my y value doubles each time. The blue one is tripling, and the green one is 5 times, getting 5 times bigger. Notice that they have the same y-intercept. Any reason why that's happening? Yeah?
Because 1 to any power is 1.
Any base number, you're on the right track. Any base number with what exponent?
Oh, 0.
A 0 exponent just becomes a 1. So it doesn't matter that it was a base 2, a base 3, or a base 5. They all, when you give them a 0 for an exponent, they all turn into a 1. So then if you look at like the next point, like when x is positive 1, you'll notice the red graph has a y value of 2. The blue graph has a y value of 3. The green graph has a y value of 5. All right, so they grow. If you go backwards to an x value of -1, I want you to think about what is 2 to the power of -1? 1/2. Remember, it flips the 2. So if we follow the red graph, notice that it's down here at like 1/2. The green graph is at 1/3, the blue graph, the green graph is at 1/5. When we graph these, we're going to end up graphing these 3 points, all right, because these 3 points can help us really get the shape right. What else do they seem to have in common besides the fact that they're increasing? What if we went to the left forever? What's happening here?
It's just really tiny fractions.
Yeah, it's almost like an asymptote.
It is what we call asymptotic behavior. Very good. So there is actually an asymptote that is a part of these graphs. It's a horizontal line, and it guides half of the graph. Like the other half is like growing away from, the asymptote. Tangent was the first graph that we saw that had asymptotic behavior. Every curve that we will study from now until the end of the year will have asymptotic behavior. All right, so they all have that kind of thing. So we're going to learn how to like transform these graphs. So for instance, if I take the red one and I do a transformation to it, so like right here, you're going to see that that actually moves it right and left because, right, it's a change that's up here with the x. So let's see, this point right here that was our y-intercept moved 1, 2, 3 places to the right. Our 1/2 point right here moved 1, 2, 3 places to the right. And our point where it was a y value of 2 moved 1, 2, 3 places to the right. Okay, so we're going to do that kind of movement with our curves. So then what about something like this one? Tell me what you notice about these 2 curves.
It's the same.
They're kind of like the flip of each other. Do you see that they're perfectly symmetric? Right, if we fold it like along the y-axis. So they are a reflection of each other. If you look at their equations, one of them is growing by a factor of 2. One of them is shrinking by a factor of 2. So they are kind of, one's growth and one's decay is what we talk about. The purple one is decaying. As you read it, it's falling flat. But if I just took the red one and I did an X flip, it would be the same. Okay, so sometimes we can take a growth curve, the red one, just do a specific transformation of a flip, and it turns into a decay. What else? Ooh, what about
So,
this one?
wait, does that mean a reciprocal would flip it over the y-axis?
If it looks like this, 2 to the negative x, it ends up being a decay.
But you had the y equals 1/2 to the power of x highlighted.
Yep.
So that's just the reciprocal too.
Correct. Because what if you considered the negative x as being 2 to the negative 1x? You went ahead and applied the negative 1 to turn it into a 1/2 and then raised it to the power of x. Yeah, so they're the same. And that sometimes it's kind of weird because you're like, well, I thought it was a growth function. Well, it is, but it's decaying. Now, what about this one? This blue one that I added on here, also symmetric, but in this case it's symmetric up to down. So we just took the red one and flipped it down.
It's the y. X.
So is this still growth or is this decay? This one can be a little bit tricky. I want you to think about roots. In what direction do roots grow?
Down.
Down, primarily. So there are things that can grow negatively. That blue graph is growing negatively. Debt grows in a negative way. So this blue one is still growth. It's flat and then it grows away from the asymptote. So both of these are growth. This is just negative growth. This is positive growth. All right, so I just wanted you to see those curves one more time before we started graphing them ourselves. So,
Will this be on the test?
tomorrow, I'll give you one guess.
No.
No. Good guess. Okay, when we are graphing these, hopefully you're looking at this equation and you're going, okay, this looks a little bit familiar. I've seen H and K before. Okay, I've seen an A before. We need to talk about the B value. This is our base number. And there are a couple rules about the base number. The base number will always be positive. Okay, does it make sense to have a negative base number? So if it's growing negatively, it's because there was a coefficient that was negative, not because the base number was negative. The base number will never be a 0 because something can't grow or decay if it actually has a value of 0. Okay. The base number will never be a 1 because if you're just magnifying something by 1 over and over and over, it's not growing or decaying. All right. And then what we're going to see is that when the base number is sort of a fraction, that is a decay function. When it is bigger than 1, that is a growth function. This A value is exactly what it's been in every other graph. It's a vertical stretch or shrink or flip. Stretch or shrink or flip. And the flip would be if it looked something like this, negative, 2 to the x. Right? That negative is not on the 2. This is a 2 to the x with a negative 1 in front of it. Okay, so the base number is always positive. But this will end up growing negatively, like the debt or the roots. All right, the H value is kind of what we've seen before. This is a X movement left or right. Opposite sign rule, like we've always seen. Opposite sign rule. And then this last one, the k value, that is still an up-down. But for this particular graph, one obvious thing that it does is that it moves the asymptote. It moves the entire curve, but the most obvious thing that you'll be able to see is that it moves the asymptote. So it moves the horizontal asymptote. Both of those words are kind of long and hard to spell, so from here on out, we will abbreviate that as HA. Ha! Okay, I'm not laughing at you. I am just saving myself the effort of having to write out 2 complicated words. All right. The equation of the horizontal asymptote is always y equals k.
Oh, so it's like the middle.
What's that?
It's kind of like the middle.
Yeah, exactly. Yeah. All right, so let's try it out. Now, before we try it out, I do want to see if we can kind of agree on some, like what should be on your graph. As we discussed, I want you to plot 3 key points. That will always help you to get your shape correct. For the sake of an example, I'm going to pick base 2. It won't always be base 2. It'll be some other base number. Could be some other base number. Now, I want to pick really easy exponent values. I get to choose these x points. So what's a really easy x value to use? 1. And then how about 0? Now, I need one more. How about -1? Now, could we use a 2? Yeah, but what if the base is a 5? And then we use a 2, all of a sudden we have to plot a y value of 25, and it's way off the grid. So instead, let's go with a -1. So therefore, if I build my parent t table, I will have a 2, a 1, and a 1/2. All right, so when you graph, we do want to see these 3 points. We want to see our curve with arrows on both ends. This part of the curve should flatten out. Onto the horizontal asymptote. And then oftentimes we will ask you to kind of show that horizontal asymptote. That's supposed to be on 0. So if you have a highlighter, you could just highlight it. You could do a little dashed line like this. And then sometimes we ask you to label it. So you would just say y equals 0. I do want to just make you aware that the answers, or sometimes when we make these graphs and we present them to you, what you'll notice is that the horizontal asymptote doesn't go on forever. And that's because some mathematicians feel like while this is asymptotic behavior, it is not asymptotic behavior going on in both directions. So since the asymptotic behavior only happens on this side, we only keep the asymptote drawn on that side. Because over here, it's growing away from the asymptote, so we kind of don't extend it. So I just wanted you to be aware of that. One thing you should always notice from that middle point, the 1 point, like 1 point over, will grow up by a factor of 2. Or if the base number is a 3, it'll grow up by a factor of 3. 1 point in the other direction will shrink by a factor of 3, or a factor of 2. So sometimes if you can just find that y-intercept, you could just plot the other points by just taking the y value and doubling it, or halving it. All right, that could be one quick way to graph. All right, so then let's try this one. This one is fairly basic. What is this going to do, though?
Flip it.
Yeah, it's going to flip it. It's going to be a flip in the x direction. All right, now our horizontal asymptote didn't move. K is equal to 0, so y equals 0. And our y-intercept, we could go ahead and calculate that by just plugging in a 0. So this would be 2 to the -0, which is 2 to the 0, which is a 1. Okay. So if I want to start there and it's a relatively simple graph, you might be able to just graph your other 2 points knowing that it's a base 2 and one side is going to go up by a factor of 2, one side is going to go down. What you do need to keep in mind, however, is that this one did flip. So it's actually going to go up on the negative x side. So when I go over one value of x, instead of going up 1, I'm going to go up 2. And then this would be a half over on this side. And so here's our curve. And there you go. All right, this one moved in the x direction. In this case, it's going 2 to the right. Our horizontal asymptote, we don't have anything added here, right? Plus 0, so this is just y equals 0. So there's my horizontal asymptote. My y-intercept, I kind of need to calculate this. If I plug in a 0, I'm going to get 3 to the 0 minus 2, so 3 to the negative 2. Now I'll have to remember our exponent rules. 3 to the negative 2 is a 3 getting squared and flipped. So 1 over 9. When you go to plot that, just do your best. Just put it, really close to 0. All right, so what we want to do is grow by a factor of 3. Okay, so one thing you could do is just take this y value and multiply it by 3. And what would we get? 1/9 multiplied by 3 would be 1/3. Okay, so my next point over is at 1/3. My next point over, 1/3 multiplied by 3 becomes a 1. And then my next point over, a 1 multiplied by 3 becomes 1, 2, 3.
So it's kind of like you're moving the y-axis over to...
However you want to think about it, yeah. There's my 3 key points. Here would be an alternative approach, because if I just lost you on that, here's an alternative approach. Start with a parent t-table. Okay, this will work all the time, and in fact, I'm going to use this approach on the next graph. So parent t-table means I want you to strip away all of the h's and the k's and the a's and make your table. So that basic table would be a 1, a 0, and a negative 1, which would give me a 3, a 1, and a 1/3. Then look and see what changes were being made. And in this case, it's 2 to the right. So is that an x change or a y change? An x change. I'm going to add 2 to all my x's. So this becomes a 3, this becomes a 2, and this becomes a 1. And you'll see that, in fact, those are the exact points that we already had plotted. Over 1 up a 3rd, over 2 up 1, over 3 up 3. So either of those approaches works. Here's your curve. And you are all done with that. Okay, so this one has quite a bit more going on. So I'm going to do that t-table approach again so that you can kind of see what to do, especially when there's a stretch and a flip and a right or left movement. All right, horizontal asymptote. I still don't have anything added, so it's still at 0. Y-intercept, if I plug in a 0, let's see what we get. We would have a negative 2 times a 3 to the 0 plus 5. Oh boy. Negative 2 times 3 to the 5th. 3 to the 5th is a very large number. 3 to the 4th is 81. So it's 243 times negative 2. So negative 486. Goodness, this is growing very fast. All right, I obviously cannot plot that y-intercept. All right, so I am going to use the basic equation, y equals 3 to the x, to build a t-table. Then I'm going to move those points around. So I'm just going to have a 1, a 0, and a negative 1. And I will have a 3, a 1, and a 1/3. All right, so this right here is an x movement. This is moving 5 left. So I'm going to take all these points and I'm going to subtract 5 from them. 1 minus 5 is negative 4. 0 minus 5 is negative 5. Negative 1 minus 5 is negative 6. Then this, is that an x change or a y change? Good. So I am going to magnify all the y's by a negative 2. So that becomes a negative 6. That becomes a negative 2. And that becomes a negative 2/3. Now I just plot my points. So over negative 4, 1, 2, 3, 4, down 6. 1, 2, 3, 4, 5, 6. Over negative 5, 1, 2, 3, 4, 5, and down 2, 1, 2. Over negative 6, 1, 2, 3, 4, 5, 6, and down 2/3, so something like that. So here's my asymptote, y equals 0, and then my curve is flat and then grows down through those points. This is negative growth. Notice it's a little bit harder to sort of predict the growth on this one, because what's the, like this didn't grow by a factor of 3, did it? And then did this really grow by a factor of 3? Well, it was at negative 2, and now it's down at, negative 6. So yeah, I guess it kind of grew by a factor of 3. Okay, thanks. So this t-table approach will always work for you. The other approach can also work. All right, this one is an x flip and a down 4. Down 4 means my horizontal asymptote is down 4. 1, 2, 3, 4. The y-intercept, if we go ahead and calculate that, we would have 2 to the 0 minus 4, so 1 minus 4, or negative 3. All right, now this one, I think we could use the shortcut on this, but let's remember that this is going to be an x flip. So this one will end up looking, like that. So from here, I would have to grow, and here I would have to shrink by a factor of 2. Now, if you're comfortable doing it that way, try that out. Like if you want, try that out right now and see if you can figure out where those points would go. I'm going to show the t-table approach, and you can see if your intuition was right. Oops. Let's have some consistency here, Schumann. All right, 1, 0, negative 1, 2, 1, 1/2. I've got to go down 4 on all of these. So that's going to be at negative 2, negative 3, 3.5. And then this has to become the opposite. So the point over at negative 1 will be down 2 spaces. It'll be right here. And then this one will be over 1, down 1, 2, 3.5. So did it grow by a factor of 2?
Yes.
It did if you're talking about the distance from the asymptote. Okay, you can't use the x-axis anymore as your reference point when it moves up or down. Okay, so if you're using the asymptote, yeah, look, it was 1 above the asymptote. Over here it's 2 above. And then here it's only a half above the asymptote. So you could still use that, but when the asymptote moves, it makes it a little bit more complicated. Okay. So there is your curve, and you are good to go. All right, the last thing we're going to ask you to do is take this concept, and we're going to give you a picture, and you have to give us an equation. One of the things that will always be true is we will always tell you, hey, this is a base 2 or this is a base 3. Because as you saw, a base 3 and a base 1/3 could be the same equation depending on the transformation, depending on whether there was a flip, right? A base 3 with an x flip is the same as a base 1/3. So that could be confusing in the same way that like a sine and cosine curve could be written as a sine curve or as a cosine curve. Okay, so to avoid that, we will always tell you, hey, let's use base 3 for this. So when we do that, what you want to look for next are some of the key pieces. Like this one right here is the most obvious. The location of the horizontal asymptote gives you K. All right, so K in this equation is going to be 1. When we give you the key points, the first one should have been the y-intercept on the parent graph. So this would have been, it would have been the y-intercept. And so in this case, you can see here that it actually moved 2 spaces right. It moved 2 right. And so that's going to give you H. And then that same first point, if you look at how far it is from the asymptote, that will give you A. So distance from the horizontal asymptote gives you A. All right, so then A in this case is just 1. So now we can write our equation. Y is equal to, all right, we're going to have a 1 in the front, 1 times, obviously you don't always have to write that, but I'm going to write it in this case. You're going to have an x minus a 2, and then plus 1 at the end. All right, so you should be all set to do 9A. I'm not collecting that tomorrow, but we'll answer questions on that on Wednesday.